Hello everyone. So we're going to talk about matrices. So the first thing I'm going to do is go over definitions and proper notation for those objects. And as usual, as we introduce a new object in math, we're going to talk about what type of operation we can do with them. So I'm going to check when are two matrices equal. And then when we have two matrices of the same size, I'm going to show you how to add them and subtract them. So we're going to go over matrix addition and subtraction. And then the next operation will be, if you have a number and a matrix, how do you multiply a number by a matrix? So that's scalar multiplication. And then the biggest operation in this chapter is how do you multiply two matrices? So that's a very new operation for us. So we did not have that with two vectors, but for two matrices, under certain condition, we're going to show how to multiply two matrices. So we're going to talk about matrix multiplication. And then the last operation for matrices, very specific to matrices, is called transposition. So we'll talk about that afterwards. And then we'll go over specific things like what are the zero matrices, what are the identity matrices, which are basically the 0 and the 1 in that universe. And then very, very briefly going over algebraic property of matrices, like how do you manipulate these objects with their corresponding operations. Let's go. All right, so some definition and notation. So the first thing is definition 11.1.1. A matrix for us, simply put, it's simply a structure, a rectangular array of numbers. So we just have like a box and it's filled with numbers. These numbers in the box are called the entries or the components of the matrix. The box has a size. So the size of a matrix is described the following way. When you count the number of horizontal line, that's the number of rows of your matrix. And when you look at the number of vertical lines, this is what we call the column of the matrix. If the matrix only has one column, we call this a column matrix. And actually a column matrix is also used to represent vectors. So we might call this a column vector. And I'll be more specific about this with the example below. And if a matrix has only one row, we call this a row matrix or a row vector. But column vectors or column matrices are more important typically for us. All right, let's go over some examples. First example, suppose we have the matrix A equal to 1, 2, 3, 0, minus 1, 2, 0, 1, 0, 0, 1, and 5. That's a nice matrix. It's very nice. So the entries of that matrix would be 1, 2, 3, 0. So those would be the entries in the first row. And then in the second row, we would have the entries minus 1, 2, 0, 1. And then on the last row, the third row, we have the entries 0, 0, 1, 5. So this matrix has 3 rows. In terms of columns, if I'm reading this matrix by reading the columns instead of the rows, the first column would be 1, minus 1, 0. The second column would be 2, 2, 0. The third column would be 3, 0, 1. And then the last column, the fourth column, would be 0, 1, and 5. So this would be the first row, row 1, row 2, row 3. This would be column 1, column 2, column 3, and column 4. So for those who are familiar with the notation, because this matrix has 3 rows and 4 columns, we say that A, and because the entries are real numbers, is an example of a matrix. So we're using this M with this double spine. So 3 rows by 4 columns, and then the entries are real numbers. All right, here's another example. Suppose B is the matrix 1, 2, 0, minus 3. that's an example of a matrix with only one column where the entries are 1, 2, 3, and minus 3. So that's an example of a column matrix. So this is a column matrix. And here, as a remark, column matrices, they really correspond for us to vectors, and we already used that correspondence when we were writing general solutions of system of linear equation. But just to make it more precise here, the matrix B, which is 1 in this example here, 1, 2, minus 3, can also be viewed as a vector using vector notation. So I'm just going to use small b here. So we have a quadruplet of number 1, 2, 0, minus 3. So if we are looking at a vector and we want to use matrix notation and we want to study them as matrices, because basically matrices are a bunch of numbers, just like vectors, the correct notation for vectors are column matrices. So here, that matrix, using matrix notation, that matrix B is a matrix with 4 rows and 1 column. So sorry, 4 rows and 1 columns with real entries. And that corresponds to the vector B, where the vector B is a vector with 4 components. So the vector B here is an example of a vector in R4. And then one more example, just to have like an example of a row matrix. Suppose C is the matrix 1, 0, 2, minus 1, and 3. That's an example of a matrix with only one row. So this is a row matrix. So it's a row matrix. And that row matrix has 5 columns. So if we use the correct notation, C is an example of a 1 by 5 matrix with real entries. So a bit of notation here. Typically when we're dealing with matrices, we will use like big capital letters for matrices. And then if we're talking about numbers or scalars or like entries inside that matrix, then or those matrices, we're going to use lowercase letters for any numerical quantities. So for example, here the matrix A, see like a big capital A here for the matrix 2, 1, 7, 3, 4, 2, and or for example like the big letter C here, uppercase, for the matrix containing the entries A, B, C, D, E, F, and you see that these numbers A, B, C, D, E, F, I'm using lower cases for those entries because they're just numerical quantities. So big letters for matrices, capital letters, and then lowercase letters for numbers, typically. So just to be clear, we wrote this as a definition. So when we're talking about matrices, any numbers inside, or every time we're talking about a number, so any numerical quantities, we might use the word scalars. So scalars are just referring to numbers. And for us, unless is stated otherwise, scalars will be real numbers. And typically when you're studying matrices, the entries are real numbers. Sometimes it could be complex numbers, but in this unit, every single matrix will be containing real numbers. So again, under piece of notation, talking about the entries of a matrix, if you're looking at the entry in the ith row in the jth column of that matrix A, it will be denoted by A with a sub-index Aij, or simply Aij. So we might put the comma or not. Normally for small matrices, we use Aij with no commas, but if you have more than 10 columns or rows, then you use a comma just to make a clear distinction between the rows, the row number, which is the first number, the I number, and the column number or the J number. So for example, I have here a general 3 by 4 matrix A. So if we're using the notation that we're familiar with, so A would be an example of a matrix with 3 rows, 4 columns, where the entries are the first row, first column, A11, first row, second column, A12, first row, third column, first row, fourth column, second row, first, second, third, and fourth column, and then the third row, first column, second column, third column, and fourth column. So in general, here's an example of a general matrices. So here's my first row, second row, and the last nth row. So again here, if I'm using the notation, if you're familiar with it, so m rows and columns. So this is an example of an m by n. So if you look at the definition under, the set of all matrices with m rows and n columns will be denoted by m and by n. So since we are talking about entries, let's go back to the previous page and extract some of those entries with that notation. Like going back to example 11.1.2, if we look at the matrix A, and suppose I'm asking you what is the entry on the second row and fourth column. So example here, suppose I am asking for A24. So you have to read the first number in the sub-index here, that's the row, and then the second number, that's the column. So A24, so I'll be using red here, so second row, fourth column, that would be that entry here. So the answer would be simply 1. So on the second row, fourth column, we have a 1. So let's just put this in a low cloud. Okay. So if you want another quick example, let's work with the B matrix. Suppose I'm asking, okay, what is the entry on the third row, fourth column? So suppose I want, so a small example here, B31. So B31 would be that entry here, which is simply 0. So we get 0. Okay, so that would be the entry third row, first column, and then one more. So for the matrix C here, suppose I am trying to extract, let's say we only have one row, so the entry on the first row, let's say fourth column, so let's say this one. So the correct notation here would be, okay, so what is C14? So C14 would be simply -1. So that's the notation for entries in matrices. So the last piece of definition in that section, so it's about square matrices, so 11.1.6. So if you have a matrix A with n rows and n columns, where n is the same number, we call that box of the numbers a square matrix of order n. And the entries on the first row, first column, second row, second column, and all the way down to the last row, last column. So the entries A11, A22, all the way down to A and N are called the entries on the diagonal, on the main diagonal of A. So for example, here I have a matrix A. That matrix is an example of a matrix with 4 rows and 4 columns, so that's a square matrix of order 4. And then the diagonal entries are A11, A22, A33, A44. And here I want to really stress the fact that the diagonal of a matrix really starts from the top left corner to the bottom right corner. So there's really only one diagonal, okay, for a matrix. And here when you're wondering, like, okay, is it top left to bottom right, or you could be fooled to think, oh, maybe there's another diagonal from top right to bottom left. So just look at the entries themselves, and we really just want to keep the entries where the column and the row numbers are the same. So A11, A22, A33, A44 are the diagonal entries of that matrix. And square matrices are so important for us that the next section is just about them. And the general In general, we have a lot of operations for matrices, but there's some special operations just for square matrices, talking about determinants and computing inverses, but that's for another topic.